Hello! So today we're going to be talking about error analysis, which is a very key component of experimentation in general, but also a key component of what we'll be doing in class this year with your lab write-ups, experiments that we do, so on and so forth. So we'll just dive right into it. So the first thing we need to do is kind of establish what error is. The formal definition of error is the mathematical difference between an experimental value and the accepted value. So mathematical difference, if you kind of think to yourself, what is mathematical difference? It's another word for subtraction. So we can put this into an equation. Error is equivalent to the experimental value minus the accepted value. Another way you may write it, or even hear me say it, or write it up on the board in class, I might just say error equals EV minus AV. So it's a little bit more catchy to me. If that works for you, go for it. If you want to use the full version, you can do that too. But just any way you can memorize that, go for it. Just be aware that they both mean the exact same thing. So kind of dive into what experimental and accepted values are. An accepted value is either the given value or the most accurate measurement. It can also be referred to as the literature value. So when I'm reading a paper as a scientist, there should be a value if I'm wanting to duplicate the experiment of something I'm trying to get to. That is the given or literature value, the accepted value. And the whole point is that when I perform an experiment to try to match that value, I'm supposed to have as little error as possible. If I have a lot of error, it either means that I'm doing something really wrong in the experiment, or that scientist that made up that value in the first place is cuckoo. Okay, so this is error analysis is a way how we scientists double check each other's work and make sure that nobody's putting any false thoughts out there, and also to make sure that we ourselves as scientists are performing experiments to the best possible way that we can. So experimental value sounds exactly what it means. It's the value that's determined in an experiment performed by the observer, i.e. you. So when you perform an experiment in my class, that value that you get for that experiment is your experimental value. I will give you an accepted value or a literature value that you're trying to match. That way you can determine your error in that experiment. Percent error is a type of error that we use a lot to report in our lab reports and scientific papers and stuff like that. The main reason is that percent error, one, has units associated with it, and two, it can be further evaluated in regards to statistics. So if we're trying to determine statistically how successful we were in our experiment and so on and so forth, we can do that. And I'll dive further into what that means here in a little bit. But it is a numerical calculation that expresses the magnitude of accuracy. So going back to accuracy and precision, how close can we get to that bullet point, that not bullet point, bullseye in the middle of the target there. So the equation that is used to determine percent error is as follows. Percent error is equivalent to experimental value minus accepted value divided by the accepted value times 100%. The reason why we do the accepted value on the bottom is because we know that it should be out of what's given to us. So when you're doing a mathematical proportion, you want to do it out of what you know, out of what the total is that you're trying to search for. So that's the reason why that's there. Now, if you notice, both of these, top and bottom, don't have units. So when we times by the 100%, it gives the unit of the percent sign, which we can use to mathematically manipulate further on in our research if need be. Now, if we substitute what we know about error, which we just learned about in the last slide, we can actually fit the equation to become something like this. Percent error is equivalent to error divided by the accepted value times 100%. So either way, you can memorize these two equations. Works for me. Just make sure that you know exactly what you're doing and what you're plugging in where. But most of the time when you're doing an experiment, you have already solved the error by the time you get to percent error calculations, so it's a little bit easier to just plug the error that you solved in. That way you can do the math a little bit quicker. And again, the units of percent error is percent, so your answer should always be like 75%, 2.24%, so on and so forth. The percent sign is a unit that you should be with a number when you're reporting percent error. So, average percent error. It sounds exactly what it means. It's a mathematical average of all the percent errors associated with a single or even multiple iterations of a similar experiment. So the reason why this is important is that if you do multiple trials of the same experiment and you get a different percent error for each one, not only does it tell you what could have gone wrong in each separate trial of the experiment, but it also helps validate your conclusions. So for example, scientists may look at a paper trying to duplicate a value, and they may do 2,000 trials of an experiment. But if they calculate the average percent error of all 2,000 trials and it's 1% error, that means you're like pretty much right on the money, and that value should be right, which means that person that first discovered it is probably going to get a Nobel Prize. So it's very, very important to know how to calculate this and how to properly deduce what's going on. Because if you have 100% error in one trial and a 0% error in another trial, then that first trial probably went horribly, horribly wrong. So you got to ask yourself, is that an outlier? What did I do wrong? What happened? So on and so forth. And it helps evaluate your own experimentation as you go forward into your scientific knowledge and so on and so forth. So in mathematics, an average is also called a mean, which is something you've probably already heard of in your algebra classes. And it can be determined by the following equation. So the average or the mean of something is equivalent to the first trial plus the second trial plus the third trial, so on and so forth, divided by the number of trials. So again, where t is the trial number, n is the largest number. So trial number, a number, if you're taking the average of the numbers 1 through 10, that would be 1 plus 2 plus 3 plus 4 plus 5, all the way up to 10 on top, divided by 10 on the bottom. So what we can do is we can take this mathematical equation that you've used in algebra and fit it more appropriately to the context of our experiment. So going into that, so we can fit that equation to what makes more sense in regards to what we're doing with our experimental values. So the way I kind of say is I say the average percent error, which I just say percent error and then average in the subscript, because you could be just doing percent error for one trial instead of the percent error average for every trial, because it's not what you want to do, is equivalent to the percent error of one trial, percent error of the other, percent error of the third one, so on and so forth, up to the percent error of the largest trial that you do. If you do 5 trials, n is going to be 5. So if n is 5 here, that means n has to be 5 on the bottom. If it was 2,000, this would be 2,000, and then this would be 2,000, so on and so forth. So again, where percent %e is percent error value of a particular experiment trial, and then n is the largest experimental trial number. So let's do an example. So let's suppose I was doing an experiment, and I was performing an experiment in which I was neutralizing 25 milliliters of 1 molar hydrochloric acid, which is 1MaCl, with 1 molar sodium hydroxide, 1M NaOH. The literature value of sodium hydroxide needed for the neutralization is 25 milliliters. Do I expect you to know all these fancy terms? No. But at the end of the year, if you go back to this video, you should be able to read it and be like, oh yeah, I know what he's doing. So don't worry if you don't know the vernacular of this. I'm just trying to simulate what you may be seeing and hearing in an experiment. Hang on one second. All right. So my results were as follows. So I did 3 trials of an experiment where I was neutralizing an acid with a base, and I found my experimental volume in milliliters to be 27.5 for one, 24.25, and 25.05. And again, the accepted volume of sodium hydroxide that was needed for it was given to me in the problem. It was right here. So my accepted volume is going to be the same for all 3 trials because I'm trying to get to that value in all 3 trials. One thing you can kind of take from this, when you're doing experiments, when you're setting up a table to describe your results, you want to have a title for each column, but you don't have to put units in every single box. What you can say is you can just put the units in the top of the column. What this says is that all these values are associated with milliliters. So 27.5 milliliters, 24.25 milliliters, 25.05 milliliters. Same thing over here. The trial number, there's no units associated with it, so it's just 1, 2, and 3. So using the data that's provided, calculate the following values for the experiment. So error for each experimental trial, percent error for each experimental trial, and the average percent error for the experiment. So what I want you to do is pause this video, take out a sheet of paper and a calculator, and see if you can determine all 3 of those values and put it into a table form that you can help present your results in your error analysis. So take a second, pause this video, and then we'll go over the answers here in just a second. Alright, so hopefully you did the calculations on your own, because otherwise this is not going to make any sense at all. This is just a way to check your answers. So the following calculations are the correct values for the example experiment. So what I should have gotten in trial 1 is I have an error in milliliters because each experimental and accepted value is in units of milliliters. So since those milliliters are not divided by each other, they do have a unit to themselves. So you should get 2.5 milliliters for the first one. And then when you plug it in, you should get 10% error with a percent sign, and your average percent error for all 3 trials should be 2.4. Now, again, you can have negative numbers in error. What that means is that you probably undershot the accepted value instead of going over it. And that's completely fine. It's okay to have negative numbers, because when you go to do all the calculations, I mean, you can't have a negative average percent error. It just tells you as a scientist, did you overshoot it or did you undershoot it? And that helps, you know, demonstrate your experimentations, and if you were to do this experiment again, how you would fix that, or at least give you a starting point of how you would fix that. So don't worry. If you didn't get the correct values on the first time through, Hakuna Matata. Yes, that is a Lion King reference. And yes, I'm not that old. Yeah, it means no worries, okay? That's the whole point of practice. So don't worry if you didn't get it right. That's the reason why we're going to try to do as many experiments as possible. That way you get more hands-on experience on what you're doing, what it means, how do you report it in a science write-up, so on and so forth. So don't freak out. We will get into that. But Hakuna Matata, that's right. Lion King for the win. All right, let's work through the calculations for trial 1 together, though. So we'll just break this down just for trial 1, just to make sure to see maybe exactly where you may have went wrong. So trial 1, error, just plain error. We know our error calculation is error equals experimental value minus accepted value. So if you take the numbers that you have from that first table, you should have plugged it in as 27.5 milliliters minus the 25 milliliters. Now again, since these milliliters are being subtracted, they're not being divided, those milliliters do still stand. And since they're the same unit, I can subtract them. Okay? If this was liters and this was milliliters, I would have to convert one of them to even do the subtraction. Okay? So that's where you get the 2.5 milliliters from for trial 1. Trial number 1, percent error. I know that my percent error is equivalent to the error that I just calculated divided by the accepted value times 100%. So you should have plugged it in, had 2.5 milliliters divided by 25 milliliters. Since this milliliter is over a milliliter, they cancel out. Just like numbers do in mathematics, units do the exact same thing. So these units cancel out. Where's my cursor? There we go. And these units cancel out, and that's how you get the percent sign for your actual answer. So again, you should have gotten 0.1 times 100. After you do this here, you should get 0.1 times by 100%, you get 10%. All right, and lastly, experimental average percent error for all of them. So again, this is doing it. So this is assuming that I've already done the percent error for 2 and 3. My equation will fit to this. So again, n becomes 3 because that was the highest number of trials that I did. So I end with my third trial of percent error up top, and 3 is going to be on the bottom. So I plug them in. 10% plus a negative, so it's going to be 10 minus 3 plus 0.2 divided by 3. So you should end up with 7.2% divided by 3, and then that's how you get 2.4. All right, so that's the end of this video. Again, if you have any questions or anything, feel free to come talk to me, email me, whatever. Don't worry about it if you're not getting it the first time through. We're going to have plenty of practice throughout the year, but please come talk to me to get any clarifying questions. I'll do my best to help you in different contexts if we need to, and so on and so forth. But thanks for joining me on this video. I hope to see you in the next one, and I hope to see you in class. Bye.